Okay, so today we're gonna do the finite element model using Femap of the base excitation problem. So let me open here some of my notes. So basically this is to use this class notes over here. Without going into too much detail, this is base excitation. So we're solving this type of problem. So you have a mass, spring, and damper. The base is moving. This is used a lot for machinery, but in our case, we're going to use this for the like if it was a car. Okay, so if you want, you can just look at this. This is a derivation. All right, with some algebra steps. Don't have to worry about too much of this stuff. And basically, the problem we are solving is this one over here. All right, so we consider this a car or an automobile traveling over a rough road. So there will be the base excitation. All right, so this is the road, this is our wheel, this is our spring, this is our damper, this is the mass. Okay, so for a mass of 600, I'm just going to do the 610 kilometers per hour. You want to find what would be the deformation. All right, so here I do the detailed calculations. This is the frequency of the car, okay, of the K over M. And this would be the force frequency of the road, this one over here. All right. So basically, for the first case, we get X equals 0.0572 for M equals 600 and a velocity of 10 kilometers per hour. All right. And here you have some unit transformation done for the velocity. Okay, so we go here to model. First thing we're going to do is to create the two properties. So first one, we're going to create the mass property. And let's see, what is that? Lane element shear laminate plot. Okay, here we go. Mass property. And this is 600 kilograms. If you want, you can put titles. Generally, I don't, but I mean, just for the sake of the example, let's just put over here. All right. So this property is created. Next, we're going to create the property of the spring. So you have different options, but this is the one I'm familiar with. But you see these different options here. I haven't used these ones really. But here, this should give you access to the C-bush element you see over here, which I'm pretty confident. So we're going to generate the spring on the y direction. So we want to put the properties on the y direction. And according to the problem is 40,000. All right. 40 kilonewtons per meter. The damping is 0.1. The initial mass is 600, and the initial deformation of the road is 0.05 meters. All right, so I have this. I will explain something about the damping a bit later, but for now, let's just leave it as it is. And maybe let's put it over here to make sure it's on the orientation. Okay, so we did the properties. The next thing we need to create is the function for the road. So we do here versus time. So let's say sine road function. So here we're going to use one equation. And I did some periodic calculation, and basically to have more than two cycles to 5.4 seconds for a time step of 0.05. You will understand this now as soon as we get the figure. And I'm going to put the magnitude. I will put it on the force. So here I'm just going to put sine, and you need to put this in degrees. So 360 times the frequency in hertz of the road. So this is, let's see here. So this is this one over here. Frequency of the road. I explain how it's done. So it is 0.4 0.463. Back on here, 0.463, 0.463, and then Femap, in order to recognize as a variable, you need to put that exclamation sign and then the value of the variable. You close the parentheses, you click add, and you see the reason I selected 5.4 is that we have at least 2 cycles, so 1 and 2. Okay, you can do 1 should be enough, but for the sake to show that. So basically with that time step, I did some preliminary try and error, and I found out that this was enough. Then this is something that I do every time. You don't have to do it, but sometimes it can help you not to create problems, to make sure the last value here is 0, so that we start from 0 and we finish in 0. You can change this one to 0, but generally what I do should not change anything. I'm just gonna add, let's see here. All right, so why don't want it to let me add one value, single value, add 5.4005. I'm going to put the value of 0. You will see it should not change at all the function. Add it just to make sure it's going to finish at 0. And okay. Okay, so basically we got almost everything we need. Next, we go to model node. We're going to create a node at 0, 0, 0, and another node at 0, 1, 0. It doesn't matter. You can put 1, 1/2. It's just that it's better for the model. You can even put everything on the same node. And okay, Control A. Oops. Okay, so 1 is here, 1 is here. Now I'm going to do model element spring. I'm going to go from this node to this node, and okay. All right, I don't know why you cannot see here the mass. So actually what you need to do is go here, double click on it, and do the same thing again, model element, then it will show up, and you select the top node, and basically you have here the mass, the damper, and the spring. We haven't set up the value of the damping yet. All right, so next thing we need to do is model constraint nodal, and let's say here fix, and here you go fix. All right. So why do I do all this stuff? Is really because if you go here to this basic, you can find this online. This is the basic dynamic analysis user guide. Basically, I went to the example here to enforce motion, and it tells you here that you can specify enforce displacement, velocity, or accelerations. And in order to do that, you see common application is earthquakes, excitation applied for machinery, building, and so on. Okay, so I'm not going to go through this. The other thing you might be interested to look at is section 3.3 for the damping. And basically here, the only thing I want to point out is that you see that the damping ratio is 2 times G over here. And this is B over B critical or C over C critical. All right, let's go back to this model. So we fixed this. Now let's apply here the force displacement that is going to correspond to this rod over here. So model load nodal. So let's say here you can call this force displacement. Okay, select this one. Okay, can put the title again. So here make sure you select displacement. Here you put the magnitude of 0.05, and that you choose the function we selected before. All right, cancel. So that's basically about it. Now model load dynamic load. You can do this now or later on. when you apply the analysis, direct transient. And this is where it gets a little bit tricky, is that, so I make some notes over here. You want to look at it. So basically, you see these ones here. So it's always going to multiply. So if you use the G, you need to put instead of 0.1, 0.2. And you see that if you define the G, you need to put the parameter W3. And if you define it within the property of the Bush element, you need to define the W4. So I always put here both of them, but let's try, but just put it on W3 in this case. So if we do it this way, here you're going to put 0.1 times 2 will be the 0.2. The damping here is 0.1. All right. But you need to multiply by 2. And then the frequency. So this is the natural frequency. The natural frequency of our system is 8.1649. But the one this in hertz, you need to divide by 2 pi. If you want here, I did in MATLAB the classic solution. All right. See, that's basically the same values. So here, let's see, let me get the screen. We were looking at omega divided by 2 divided by pi. And this is 1.2995. So I'll come here and I put 1.2995. I mean, that should be enough, but I always put it here, both places. Now, this is also the other part that is important here. Make sure you use the same time step that you have been using to create the load. So our time step was 1/200. The number here, put 1, you don't have to put it, but it works better. And the number of steps here corresponds to the length of your vector. So again, if you go here to MATLAB, I did it over here. If you see time step 1/200, final time 5.4, you can put 5.005. It doesn't matter. And then what I do is run this, and I'm looking at the length of T. So let's say this one, let's call this one DDD, so it's clear. Run it. And it's 1081, 1081, 1082, 1081. So you come here, number of steps 1081. You can put 1080 if you want. 1081 and direct. All that stuff looks okay. So remember this screen because it's important. All right. Now you go here to analysis, or right here, right click, manage new. Here, make sure you select dynamic transient. So this is on Femap, they call it solution 3, but really this is in NASA, I think it's solution 106 or 109. All right, so here you need to be careful, edit. So next, 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 next. I think it's the screen. No, the next one. All right, here you see use loads. You could define here the initial values for the time integration, but we did it before. So use loads set options. And that's all you need to do. And analyze. And I'm going to pause because it takes about 2-3 minutes to run, or about 2 minutes. Well, so actually it run pretty fast within a few seconds. So I'm going to close this. Now, if you look at the data, this is transient. So you should see all the different solutions. Okay, so best way to look at the data here is to click here, that little figure. And then we're going to select here the data series, new data series. So we're going to plot versus a set, is there an entity? If you put here, we'll put the 10,080. If you put here, we'll put the time. So it goes from time 0 to 5.05. We want to click the T2 translation, and at which location will be this one here at node number 2. So that would be how much really, if you are the passenger in the car, how much you will be feeling. And okay. And basically, this is the answer that you have. All right, so you see before you go 0.7, and then after the second cycle, is going to stabilize at about 0.05. It's really 0.5072, I think it is. All right, it's about that value. Okay, so here you have this curve. If you want, you can save this data into Excel. Okay, you can do whatever you want, but here's about that value. Now, if we look at the classic solution that I had over here, this is the solution, this is the load. So you see, this is the form, but this is already the closed form solution. So you see, gives you this part already after the first cycle. And the magnitude of this, so from here to here, is 0.0572. And here we get really, so really in order to get the value, let's see, we can do this. All right, so let's not do that. Let's just close this for a second, or let's leave it here. F5, I don't want to go to Excel and do it. Let's do it over here. Let's look at the criteria and the T2 on the contour. Okay, criteria, okay. So this should give you the values. So it should be about this height. So I think I checked before. So here you put is 5.5675, 5679, 5682, 5684, 85, 84. So max is about 974.05685 as compared to 8.572. So it's extremely close. You could get a bit closer if you do the time step smaller. What happens is that maybe right where is the top, we don't have a point. But I mean, to me, this is accurate enough. Okay, this is less than 1% error. So let's go back a little bit about the damping. So let's save this model here. All right. Okay, so let me just here delete this data. So here, shift all the way up. Delete. Okay, let me do. Let's say this one as model 2. Save, and this time what I'm going to do is change the location of the damping. Okay, so in this case, what I'm going to do is, let's see, model, load, dynamic analysis. I'm going to eliminate this one. All right. And I'm going to put it over here. So again, you need to be careful here. 0.2, you need to multiply by 2. And okay. Let's put it over here, actually. And okay. File, rebuild, yes. And analyze. Okay, so this one took a bit longer. But again, you can do the same thing. You can look at all the results. Best thing is to come over here. And he did it right away. You see, you get exactly the same answer as expected. Again, make sure you don't put in here twice the, you put it here and the other place, because then the damping adds up. So basically you are having twice the value of the damping. All right. So that is something you need to be careful. Okay, something like I mentioned before, we did it here, but otherwise you can come here. You can copy the values. Yeah, do this, copy the values. You open an Excel. You come over here and then you can just come here, insert, and that's not what I want. Probably want one of these ones. So not this one either. There you go. Should be one of this one. Hopefully this one. All right. So you see here, you can delete all this stuff here, but basically about the same size. And here you can probably read the value here. Let's say you can just put equal to max value of B to B, whatever, I'm guessing 1082. Even if it's 0, doesn't matter. Oops, what is in here? 0.069. So actually we'll give you this one here. So maybe let's change that from B, let's say 1000. Strange. So we have before the 976. So let's see, it would be, why do we have so many values here? Oh, wow. Well, anyway, if we come here, I think we just copy them twice. Yeah, I have them copy them twice. So why did you do that? I don't know. But that's the problem. Let's erase from here down. Oh, I know why it's twice. Sorry to make the video long over here. Almost there, 4 seconds. There we go. So basically you see it over here. What happens is that we have here the two curves. So it did that. So let's say now here. So let's look here, what's about 0.0. Five, 5, 6, 5, 6, 3, 5, 6, 1, 5, 6, 8. Okay, probably this one would be the highest one, or this one around here about 0.979. All right, so basically that corresponded here, I think, to the point that was, what was it, 974, 975. Let's say 0.5685, 84. Yeah, so 0.5685. All right, so thank you for your attention. Just want to add one more thing, guys. In case you did not see this page, just want to there's some good comments on it. All right, so just read it. And I'm going to end the video.